Okay, so we've looked at reflections, x-axis and y-axis. We've looked at shifts, horizontal and vertical. Now we're going to look at stretching and compressing our function. Okay, so to do that, we're going to again go back to our good old f of x equals x squared. And we're going to start by looking at what happens when we multiply by 2 and multiply by 1/2. So just like before, we're going to start by plotting some points and taking a look at what goes on here. So I plot -1, I'll have 2 times -1 squared. -1 squared is 1, 1 times 2 is 2. So I have the point -1, 2. Plugging in 0, I'll have 2 times 0 squared. 0 squared is 0, 0 times 2 is 0. So I also have the point 0, 0. Plugging in 1, I'll have 2 times 1 squared. 1 squared is 1, 1 times 2 is 2. Whew, so I also have the point 1, 2. Now, when I sketch the graph, notice that I get kind of a narrower, more skinny parabola for the graph of 2x squared. Let's do the same thing, but look at what happens when it's 1/2 x squared. So plugging in -1, I'll have 1/2 times -1 squared. -1 squared is 1, 1 times 1/2 is 1/2. So I have the point -1, 1/2. Plugging in 0, I'll get 1/2 times 0 squared, which will be 0. Plugging in -1, oops, I had -1 twice. This should be +1, huh? So I'll have 1/2 times 1 squared. 1 squared is 1, 1 times 1/2 is 1/2. So when I plot those 3 points, notice I get a parabola that's sort of wider than my original parabola. When I'm multiplying, and again, I'm multiplying outside here, I'm getting vertical stretches or compressions, okay? Your book just calls these stretches, so this would be a stretch of 2 or a stretch of 1/2. Other places will refer to this as a stretch of 2 and a compression of 1/2. I like the stretch and compression because it kind of makes a little bit more sense to me. One way I think about this is if I take my original function x squared and I stretch it up to 2 times its height, it's like I've taken my function and I'm stretching it up. That makes my function a little bit skinnier, so it kind of stretches it up this way. Compression, it's like I'm taking my blue function, I'm squishing it down, or I'm compressing it on the top, and it kind of widens out my function. If I push down on my function, it's going to widen out my function. So these, again, are representing vertical stretches and compression. Okay, so vertical stretches or stretches and compressions. Okay, multiplying by something bigger than 1, so something like 2 is going to give us a vertical stretch. Multiplying by something smaller than 1, like 1/2, is going to give us a compression. Okay? Now, if we can vertically stretch and compress our functions, guess what? We can also horizontally stretch and compress our functions. So let's use our square root of x function to explore that for a minute. All right, so to explore this, we're going to look at square root of 4x and square root of 1/4 x and see how that changes. Forgot to put up our original graph. Our original square root graph looks something like this. So there's our original square root of x. And now let's graph these multipliers. So square root of 4x, when I plug in 0, I'll have the square root of 4 times 0, which is the square root of 0. So I'll have the point 0, 0. Plugging in 1, I'll have the square root of 4 times 1, which is the square root of 4. Square root of 4 is 2. So at 1, I'll be up here at 2. Plugging in 4, I'll have the square root of 4 times 4, which is the square root of 16. Square root of 16 is 4. So then I also have the point 4, 4. Okay. So there's our graph of the square root of 4x. You can see that that looks different than just the square root of x graph. Now let's compare that to the square root of 1/4 x. So plugging in 0, I'll have the square root of 1/4 times 0, which is the square root of 0, which is 0. Okay. Plugging in 1, I'll have the square root of 1/4 times 1, or the square root of 1/4, which is 1/2. So I'll have the point 1, 1/2. Plugging in 4, I'll have the square root of 1/4 times 4. 1/4 times 4 is 1, so the square root of 1, which is 1. So I also have the point 4, 1. Okay, so now if you look at these are also representing stretches and compressions, only this time they're horizontal. So you can think of with this graph, it's like I've squished or pressed against the graph this way. So this is pushing our graph this way. So this represents a horizontal compression. Whereas this guy, it's like I've taken it and pulled it out. If I pulled here, it's going to stretch this out. So that represents a horizontal stretch. So both of these are representing horizontal stretches. And again, your book is kind of going to use that term stretch, which means my math lab is going to use that term stretch. Okay. So we can now vertically and horizontally stretch these guys as well. Okay. Now, the other thing I want to do here is I want to put kind of all of this together and look at what we've done all together. So I'm going to take a pause, erase this, and kind of summarize everything that we've done so far. All right. So here's everything we've done so far in terms of transformations. We looked at reflections. X-axis reflections, where we put a negative out in front. Then Y-axis reflections, where we put our negative inside. So, not like that. Wow, I had that written wrong. Glad I'm going over it. Y-axis reflections, our negative is inside with our variable. So square root of x compared to square root of negative x. Shifts, we can shift horizontally, that means left and right, and we can also shift vertically, up and down. So horizontal shifts, we're going to add and subtract inside with our variable, and they sort of work backwards. So notice here we're adding 1, that would be a shift left of 1. If we subtracted 1, it would be a right shift of 1. We can also move up and down or vertically, and there we're subtracting outside. So something like the square root of x plus 3, those work the way we sort of want them to. Plus 3 moves up. If we wanted to move down 2, we would do square root of x minus 2. Stretches and compressions, we can do those again vertically and horizontally. So I can stretch vertically, I can stretch horizontally, or I can compress vertically, compress horizontally. Okay, vertical stretches are outside multipliers. So we're multiplying kind of in front of everything. So such as x squared and 2x squared or 1/2 x squared. That's going to be a stretch if our multiplier is bigger than 1, and it's going to be a compression if our multiplier is less than 1. And then horizontally, we're multiplying inside. So the square root of x compared to the square root of 4x and the square root of 1/4 x. With those things, we can sketch a graph of most any function that's in transformed form. So what do I mean by that? Well, let's say we're asked to sketch a graph of this function here. Okay, so we're going to sketch the function f of x equals -3 times x plus 2 quantity squared minus 4. Now the first thing we need to do is we want to identify the basic shape of this. So what do we mean by basic function shape? Well, we're asking, what have we transformed here? We know 2 different basic function shapes right now, x squared and the square root of x. Well, this is a basic x squared graph. In other words, the basic shape of this, before we transform it, is that basic parabola, that basic U shape, okay? So the basic shape is that of the x squared graph. Now what we need to do is we need to identify all of the transformations that have been done to this graph, okay? In other words, what's different from x squared to this graph? Well, the first thing I see is I see this negative out in front. What does a negative out in front do? Well, a negative out in front is an x-axis reflection. So this graph has been reflected across the x-axis, okay? Next thing I see is this 3, this multiplier. Now this multiplier is outside, so this is going to represent a vertical stretch. So this is a vertical stretch. Okay. Now we've got this plus 2. That plus 2 is inside with our squaring, so what is that going to be? Well, that's going to be a horizontal shift. And that's going to represent a horizontal shift of left 2. And last, we have this minus 4. This minus 4 is outside of our squaring function. So this is going to represent a vertical shift, and that's going to be a vertical shift of down 4. All right, now with all of that, we can sketch a pretty decent graph of this guy. Now, what do I mean by that? Okay, so notice that I'm going to use the word sketch here. So when I sketch, I'm really thinking, okay, it's going to be a sketch. I want to get basic shape and basic location of this graph. Okay? So what am I going to do? I'm going to take my original function, which was here, and opened upward, and I'm going to do all these things to it. So first of all, when I reflect this across the x-axis, this graph is going to open down. So my reflection will make my graph switch from opening up to opening down. Okay? What else have I done? I've shifted this graph left 2 and down 4. So over here, I'm going to go left 2 and down 4. Okay. And last, we've stretched this. So when I draw it, I'm going to draw it stretched out. So here is a nice sketch of this graph. It's got basic shape, how it opens, and also basic location. Okay? So that's how we can use these transformations to sketch graphs. Let's do one more example. All right, let's work one more example. So we have f of x equals negative square root of negative 3x minus 2. Okay, so first thing we want to do is think about our basic function. So what's the basic function that we're transforming here? Our basic function is the square root of x graph. And the basic shape of that basic function is this. So we're going to transform that shape. So let's look at what's been done to our basic function. We have a negative out in front. That's an x-axis reflection. We have a negative inside. That's a y-axis reflection. This 3 multiplier inside is a horizontal stretch or compression. Remember, my math lab just refers to these as horizontal stretches. A minus 2 outside is a vertical shift down 2. Okay, so now we're going to take all of that information and we're going to sketch a graph. And again, remember we're using that term sketch because it doesn't have to be perfect, just has to give us a general idea and general shape, okay? Okay, so first let's think about, we have an x-axis reflection, which would do this. We also have a y-axis reflection. So when we've done both an x and y-axis reflection, our final shape, the shape we draw, is going to be this. And what else have we done? We've got this, right? Horizontal compression, so we've pushed this back. It's going to kind of be a little bit like this. And then we've gone down 2. So we're going to go down 2, and then I'm going to draw that basic shape horizontally compressed. So something like this. Now again, this is just general, it's not perfect, I'm not plotting points, I'm just getting a general idea. The only point for sure is this guy right here, and that starting point that I've shifted around. The other thing to think about, once we do this, one nice reason to sketch graphs is it makes it a lot simpler to find our domain and range of a transformed graph, right? From here, we can look at this and decide what our domain and range are. Our domain would be negative infinity from here all the way to here to 0, including 0. Our range would be negative infinity to negative 2. So one nice reason to sketch graphs of transform functions is to think about the domain and range. All right, so again, we've got reflections, shifts, and stretches and compressions. With this, we can sketch any transformed function. So once we have the basic shape, once we know a function's basic shape, as long as it's in transform form and we can identify the transformations, we can get a nice sketch of that function.